Okay, we're going to continue our study of the covariant derivative. And last time we ended up with a pretty good definition. We called the covariant derivative, and I'm going to start changing these indices to something more Greek, right? The covariant derivative, expressed as del with a space-time index in the bottom, of a vector, say x alpha, is defined as the partial derivative of x alpha plus this very critical term involving the connection coefficients, alpha, gamma, mu, and x. We're going to sum over gamma, right? And that is the covariant derivative of the components of a vector field, right? This is the vector field, and I'm no longer going to point out that x alpha is a function of x. It is a vector field. What's interesting is today we are going to talk about a situation where you do need to have a field and a vector at a point, but we'll make those distinctions clear, and we'll reintroduce this x when we need to. So, and also, of course, these gammas, they're also functions on space-time as well. And we learned that these gammas were how we determined the notion of parallelism. Without them, you can't determine what's parallel. You can't understand how the rate of change between two different vector spaces can be measured. And these are sort of the secret guys. And what I kind of said was, what I was getting at too last time was, we do have the metric tensor field on space-time. And this is just, again, the components of the metric tensor field, right? It would be dx mu dx nu, which, by the way, is written in shorthand as g mu nu dx mu dx nu, right? They omit the tensor product, they omit that, and they omit the fact that this is a tensor field. They omit that. And this means, right, whenever you see that, you've got to think g mu nu, function of space-time, dx mu, tensor product, dx nu, where this is a map. Of course, I'm just constantly reviewing these things. But I told you that this was the thing we were discovering with physics, right? This was the big thing. And then at the end of the last lecture, I said, oh, no, physics, we use that to get these guys, because parallelism, that's a big important deal. So the truth of the matter is that the Einstein equation solves for g mu nu. Ultimately, that's the goal. That's what a space-time is. And it turns out later we will learn how once you have a metric on space-time, there actually is a naturally implied connection. Right? Once you have a metric, you have an implied connection. So one of the big functions of a metric is to give you the connection, right? But ultimately, it is the way the math is designed, the structure of the Einstein equation. Really the logical flow is you start with the stress-energy tensor. The stress-energy tensor through the Einstein equation ultimately gives you the metric on space-time, and that, if you want it, gives you the connection coefficients and a lot of other stuff, right? That the metric, basically everything then flows forth from the metric. The metric is the space-time. It is the space-time, right, is the metric. So anyway, we, understanding that eventually we'll learn how to do all this, the point is this is one of the reasons why we want to do this, right? We want to be able to take these derivatives and these covariant derivatives on a manifold, and this is the rule that we use in the case of vectors. And of course, we're dealing with the components of vectors, which are contravariant objects, right? So that being where we left off, I will point out that all of this works in a very similar fashion for taking the covariant derivatives of covectors, right? So in that case, we will write del mu, say y alpha, equals del mu y alpha. But now we get a minus sign, and then ultimately here we have a y alpha, which will sum with, well, actually here we'll have a, whoops, not a y alpha, we'll have a y gamma, which sums on a gamma, and then we have the same arrangement as before. We have the mu in the second slot, and see, what do we have to have left? We have to have a mu alpha. So then we have an alpha here, right? So this is the rule for the covariant components of, or the covariant components of a covector. And this is just the convention, right? The sign will change. Now, there's also a rule for tensors of arbitrary rank. And basically, every contravariant index will get this rule applied, and every covariant index will get this rule applied. And there's one overall derivative term, just once. And I'll express that rule a little bit later. I don't want to bog us down in it. But there are these two forms. We've proven up this one, or we've demonstrated this one. This one is just very similar. And that is where we ended up last time. What's interesting about this is the components of this object, del mu x alpha, that's a component, that object had, which can also be written as x alpha double bar mu, right? It's the same thing, right? Notationally, it's just but the subscripts are in different orders here, right? So, but they both represent the components of a 1-1 tensor, right? And you can tell because you have an up index and a down index. Now we know, I've already made a big deal that this guy here is not a tensor, and we'll talk a little bit more about that today too. But everything else around it is. In fact, the fact that this here is not a tensor is important because ultimately this is a tensor. So this is not a tensor, and this is not a tensor, but when you add them together, you do get a tensor. And that's one of the important purposes of this thing, is in order to establish a derivative object that is in fact a tensor, which means, of course, that it has the right kind of transformation properties when you transform coordinates in spacetime. So this guy here is a tensor, and I say this guy because they're both re-expressions of the same thing. And it's a 1-1 tensor, so you know that you can throw on this version of it, you can throw down, what do you throw down? You go partial alpha, tensor product, dx mu, like that, right? And then this is the component, and this is the actual basis system that you're in. And it's the coordinate basis. We're almost always using the coordinate basis when we use a basis. And so the covariant derivative takes a 1-0 tensor and produces a 1-1 tensor. So that's an important thing to keep in mind for the lesson today as we get into the more abstract form of things. And I think this is a good ending of the review, so now we'll go on to this more abstract version of the derivation of a covariant derivative. So let me start by again writing down the formula that we derived last time, which I will write in both forms. Oh yeah, that's right, I'm trying to get away from these Latin letters, so I'll go with mu, del mu x alpha plus, and this one will be alpha beta mu x beta. And so I'll use this form here, but it's also should keep in mind that this is actually the preferred form, I believe. So in fact, I'll try to defer as much as I can to this form here, but when I say I'm going to use this form, what I mean is I'm going to do the version that is dealing with the covariant derivative of the components of a vector, right? And notice they're contravariant components of a vector. And you'll notice there's also, we're not dragging around the basis vectors, right? But as I said a moment ago, this is a 1-1 tensor, so there's no reason why hanging out in the wings, you can't have you can't have partial alpha tensor product d x mu, right? You can certainly have that. And by the way, when you do this, the ordering I always draw from this form, right? This form, the ordering would actually look a little different because you have this index and then that index. So when I do think about it in terms of the mapping that it actually is and throw in the basis vectors that are relevant, I use this form. And this little bar, don't let that throw you. You still treat this index exactly like any other spacetime index. If I was to transform this is a tensor, or the components of a tensor. If I was to transform this, I would use the same, I would use the covariant transformation property to transform mu, and I would use the contravariant transformation property to transform alpha. These little bars there are just to remind you that this object is defined in this way. And that bar tells you that mu is going to show up in exactly these positions, right? And it also will tell you that alpha will show up in those positions, right? So those two bars there are kind of important. And they're usually a semicolon. I should remind you that too. When you look in other books, you'll see that as a semicolon. Anyway, so with this thing in mind, this will be our kind of, I'm going to use this as a reference as we go through the more abstract version of all this that is done by Meisner, Thorne, and Wheeler. So the book we're going to reference here, Meisner, Thorne, and Wheeler, and let's see, specifically, I actually have it out open in front of me here. It's page 254. Now let me say something about this book. The book is called Gravitation, and it's one of the more famous books in general relativity. It's a big old thick, usually paperback, black covered book with an apple on it, and it's got a lot of great appealing pictures and diagrams in it. It's actually quite a remarkable book. I picked it up early in my learning of general relativity, and I found it a little bit difficult actually, despite all of its inviting language and really tons of good examples. It was a bit intimidating for some weird other reason. I can't put my finger on it, but I can say that my recommendation is it's a really great book for a second review of the subject because it'll really deepen your knowledge of the subject. So I would start with a even more elementary book and get down the component mathematics, the component description of general relativity real solid, and then transition into this more the more abstract and pictorial versions of things and systematic versions of things that MTW does. So, for example, they do the covariant derivative in a way that starts out quite abstractly, and then they end up in the component way, which in some sense is very logical, right? Remember, the component fashion requires laying down coordinate system, choosing a coordinate system. A coordinate system is arbitrary, keeping in track that, okay, arbitrary coordinate changes won't change this equation because it's a tensor, all that kind of stuff. But on the other hand, so starting out abstractly, you throw all that away. It seems like you're throwing all that complexity out the window. The problem is it's very abstract, and it's very hard to sort of capture what you're doing. So let's have a look at his abstract introduction to the covariant derivative. So the way he begins is I should say they, Meisner, Thorne, and Wheeler, the way they begin is they define this object, and they call this object the covariant derivative operator. And they define it as a machine, right? They like to use this word machine. And they say that, hey, there's a machine, it exists at every point in space-time, and you feed this machine certain things and it gives you certain things back. And this is a machine that takes three different objects, and these are all slots, right? This will be slot 1, slot 2, and slot 3. Now this looks very much like the way we design tensors, right? We know that a tensor, say a 1-1 tensor, which would be say d alpha beta, like that, and the 1-1 tensor would have well, let's go back to our abstract notation, E alpha tensor product E beta, like that. We know that this is a, sorry about that. This is a mapping that takes two slots. It takes a slot for the first slot, it requires a covector, and the second slot requires a vector. So tensors are machines just like this covariant derivative operator is. But not all machines are tensors, and in fact we're going to discover that the covariant derivative operator is not a tensor. But it has this same feel in the fact that it has slots, right? So what goes into the first slot, second slot, and third slot of the machine? Well, we can almost guess what it's going to take, because ultimately it's got to make contact with this thing up here. So what does this thing up here have in it? Well, it has a vector field, right? So this operator, there's a vector field involved. Then there is, well, the vector field involved, and then you're left with a 1-1 tensor, right? The 1-1 tensor object here, which I've kind of thrown the basis vectors out on the side. So the next thing a 1-1 tensor needs is a covector and a vector, right? So this object here is a machine that takes a covector and a vector, but in some sense this object here takes a vector field and then produces this thing, which then consumes a vector and a covector, right? So ultimately the way Meissner, Thorne, and Wheeler looks at it is they abstractify it one step earlier than this. And they take this operator and they say, okay, it's going to need a vector field, it's going to need a covector and a vector. And in their book, the way they order it actually is they order the covector here, and they use theta for that. Let's see if I can do a better theta. Something like that? No, that's not good. How do we do a theta? Like that. Theta was for the covector. So we'll say that theta is an element of the cotangent space at a point. So it's the element of a cotangent space at a point P, right? Because the machine exists at a point P, right? So that is drawn from the cotangent space of P. And then they like to go after the vector field, and they put the vector field here in the middle, and they use V. I think I'll stick with X, right, for the vector field. Now I'm just using a capital X for this vector field, right? So X is actually an element of the total tangent space on the manifold. It's a vector field, right? So that's something you got to remember. And right away you know this isn't a tensor, because the tensors that we have worked with, all the slots require vectors at a point, right? They don't require vector fields. You don't feed you feed a tangent field a vector field, or I'm sorry, you feed a tensor field a vector field, but you don't feed a regular old tensor a vector field. And then the last thing is they want to feed it a vector. We need that vector, right? Because we're dealing with it eats a covector and it eats a vector. And so we need a vector, which they write down as u. So u, and then u is an element of the tangent space at P. So when it gets those three things, it outputs a real number, right? So when it feeds on those three things, you get a real number in the end. So we kind of think, well, how can we make a real number? Remember, there shouldn't be too many choices, right? This is supposed to be something you're kind of forced into. It turns out that real number is going to be, what he does is he says, okay, we got the one form, the element, the covector there. Well, what does it do? It eats a vector. So what we have to do is we have to take these two guys, a vector field and a vector, and we have to do something to it to produce another vector. And then that vector we'll put here, and then that form will turn that vector into a real number. So we've got to come up with a way of taking a vector field and a vector and producing a another vector. And the way he says is, well, we're not positive on how that's going to work right now, but I'm going to give whatever that is this symbol, del u acting on x. And this guy here is a vector, and it's got to be, in order for this process to work, it has to be a vector in the tangent space at P, right? So this is an element of the tangent space at P, whatever that thing is. Now, admittedly, this thing is looking a lot like this thing, but what are the differences? Well, here, this is just a space-time index, right? This is actually a full-blown vector, right? So in some sense, del u, if u is a vector, well, we know, what does that mean? That means u is u alpha partial alpha in some coordinate basis. So this thing actually could look like u alpha partial alpha, right? Because this here is a vector. It's not a space-time index, it's a full-blown vector. So this is actually a different object than this. And when you compare these things, it's easy to get this confused. And I've seen people get this confused before, somehow trying to match this up with this, not quite realizing that this is a totally different symbol, and it means a very different thing. Now, it turns out these things are highly related, but understand that right now we're just trying to build this machine. So we need some process to create a vector out of a vector field and a vector at the point. Also, I should point out that in Meisner, Thorne, and Wheeler, these here, this operator and the operators here, are all in heavy bold face, where this is in sort of normal font usually. So that's another way to distinguish these things, is through the font of all of this stuff. So this thing here would look like something really thick and black, and so same with here, it would be really thick and black, right? And the U too would be also really thick and black. Actually, all of the abstract vectors, when there's no components around, they like to make it thick and black. And then when you throw components on it, all of a sudden this becomes really thin. So they use a lot of font to play around with this idea. But we can't. It's not as easy for me to do font here on this board, so I'm not going to bother. All right, so now how would we produce this object? What do we understand that this object could possibly be? So looking at this thing here, understanding that this is a vector and this is a vector field, let's go back to this guy. We remember the derivation of this guy. It had to do with moving something that was moving a vector in a vector field, or parallel translating a vector field's value at one point to a vector field's value at another point. And ultimately we produce this thing which is a 1-1 tensor. So if we fed this 1-1 tensor, if we fed it a vector, then this part would eat up the vector, right? And it would leave behind just this part. So without this part here, right, if I took this part and moved it away, what would I be left with? I'd be left with this thing modified by whatever modification was when it ate the vector. I'd be left with something that had just a basis vector in of a vector, right? So what would be left is a vector. I'm essentially contracting this with a vector, and I'm left with a vector. That's the whole point of a 1-1 tensor, in a way, is a 1-1 tensor. A 1-1 tensor actually eats a vector and will return a vector. A 1-1 tensor can be considered as a function that eats vectors and gives back vectors. So I could take this thing and feed it a vector and get a vector back. So that's kind of close to what I'm after, because ultimately I want this to be a vector. So the way I can think about this in the machinery of what I already know is would be x alpha double bar or partial derivative with respect to gamma, right, which is a machine that takes two slots, I leave the first slot blank, and the second slot, I'm going to feed it u, which is a a vector, right? So this thing is going to end up being an element of the tangent space at P, right, which is a vector. So that's what I'm after. So how do I affect this process? Whoops. How do I affect this process? How does that actually work? Well, if we were in the coordinate basis, we would just pop u out in front and go with u gamma x alpha, oops, x alpha partial gamma, like that, right? And that thing here, if you look carefully, this gamma and that gamma sum out, so there's no gammas left. And then you're left with alpha. So this is going to be a vector, right? And notice it's got all the parts. It's got the u, there's the u, and it's got the vector field, there's the vector field, and it's actually kind of got something reminiscent of this delta because it's got the covariant derivative of that vector field. So we took the our understanding of the covariant derivative, and we took that understanding and created this covariant derivative object that we learned about, and we basically contracted it with a vector at the vector space at the point P, and that contraction ultimately is what we're after, which is another vector. So this is exactly how we're going to define this object. We're going to define this object this way. Now it seems strange because I'm talking about an abstract object that I've defined using the component system, which in components means we have to have a coordinate. Whenever I say that, you should understand when I say, oh, we're using components here, what that really means is we've chosen a basis, right? Which means we've selected coordinates because we always use the coordinate basis, right? So what I've done here is I've made a connection between this abstract notion that Wheeler's looking for, some kind of vector composed of these three objects, and I've given it a concrete realization in the basis coordinate system. And then I sort of define that abstract thing using this concrete thing. And that's not the way it's supposed to go, right? You're supposed to be able to understand things in the purely abstract and then realize them. However, I feel like I'm doing a service because I'm going through this step-by-step starting which was easy to understand, right? To the extent that this is easy. But this we understood using basically calculus, right? And so we got this picture down, and now I'm kind of trying to show you what Wheeler's getting at during his derivation. On the other hand, we could think of this as, no, we're going to just maintain the abstract idea. This is just some process that produces a vector, and we'll try to figure out what that process means later. But ultimately, this is what it's going to be. It's going to be this 1-1 tensor consuming this vector u, yielding this after the index gymnastics are all washed out, or all done. Now, like any machine, like this tensor machine we were talking about, you don't have to fill every slot of a machine. Just like the tensors, just like that 1-1 tensor, we only filled one slot, and we created a function that takes vectors and returns vectors, right? You could also just fill some of the slots, and Wheeler definitely, Meisner, Thorne, and Wheeler does that as well. So they take this object, which has its 3 slots, and we just learned how it works when you put something in every slot. But if we left the first slot empty, right, and we just put in the vector field and the vector u, well, what would come out of that is this object, right? Right, that's what would pop out. And I'll just allude to the fact that this thing is going to be u gamma x alpha gamma, like that, which is the components. That will be the components of the ultimate vector that is returned, right? And this is all an element of the tangent space. We just went through that. So that's one way of looking at this, and remembering that this is a vector field, of course, right? I can't resist pointing that out each time. And this is a vector at P, right? Okay.
But then you could also take this and you could leave the first slot blank, put in the vector field, and then leave the second slot blank. And in that case, you're going to get an object out that we're going to call del x, right? So how would that del x? How would that the gradient of x, perhaps, or ultimately it's the covariant derivative of x. I'll give all these things names in a moment, but that object, which is the result of only putting in the vector field and leaving the one form and the vector out, that is actually exactly what we defined in our last lecture. That's this thing. That's a 1-1 tensor. That's a 1-1 tensor, right? So all of the constructions that can be derived through this machine in one way or another. But this is going to be the 1-1 tensor that in the coordinate basis looks like what we've learned before. This object here is what Meissner, Thorne, and Wheeler calls the covariant derivative, or sometimes the gradient of the vector field x, right? And that's what we did, right? We called this the covariant derivative of the vector field x. This thing here needs its own name, right? And if you look at it, you're taking the covariant derivative or the gradient of a vector field x, right? You've got this object, this 1-1 tensor, and then you're kind of checking out how it operates in a certain direction, and that direction is u, right? And so by contracting it with u, which is, contracting it with u is the same thing as feeding this 1-1 tensor the vector u. Ultimately, that results in a contraction. If you go through the exact mapping like we've done many times before, you end up with this, this contraction. Maybe as a review we should do that, right? We have x alpha gamma partial alpha tensor product d x gamma, right? This is a mapping, and we feed it a blank slot, and we feed it u alpha, or u, not alpha, u beta del beta, right? That's the vector u, right? And it would be, this would be a boldface u if you could read the text. So once you do that feed, you use the so now this covector is going to eat that thing, and you'll ultimately you pull out the beta because it's linear, so you pull out the u up front, and you would get u beta x alpha gamma partial alpha, and then you're left with dx gamma partial beta, right? But this thing, of course, is the delta function of gamma beta, and that delta function then forces this beta to become a gamma, so you end up with u gamma x alpha gamma del alpha, which is a vector and the element of the tensor product space. So element of the tangent space at P. So that's just in case you forgot how we end up with this, right? And now, of course, we're just talking about the components, right? So when we do the components, we kind of mysteriously, that stuff all disappears. And we rely on the index gymnastics to keep track of what's what. And that's the way the elementary textbooks do it. And actually, I should say, not just the elementary textbooks. Some of the very advanced textbooks do that. Very few, if in fact none, of the GR textbooks actually drag around these basis vectors. I just do it because I'm a little obsessed about it, I guess. Okay, but what was I trying to say here? Oh yeah, so the name of this thing, right? The name of this object that Meissner, Thorne, and Wheeler had to define to create a vector out of a vector field and a vector, that is ultimately this thing here, and they call that the covariant derivative of vector field x in the direction u, right? A direction in the direction along u, and maybe they should add at p, right? You know, there is some implied p. And what p is it? Well, it's the p, since u is an element of a tangent space, it's whatever that tangent space p is. It's the same p. So that's what they call this, the covariant derivative of vector field x in the direction of u. You could call this maybe the directional covariant derivative, but the point is it's a vector. It's a vector. And so ultimately you have three things. You have the covariant derivative, then you have the covariant derivative of a vector field, which is defined as this is the covariant derivative operator. This is the covariant derivative of x, right? Let me do that a little better. This is the covariant derivative operator. This is the covariant derivative of x, and then you have this thing, which is the covariant derivative of x in the direction of u. This is a 1-1 tensor. This is a 1-0 tensor, right? We also call that a vector. And this thing is not a tensor. So let's talk about that for a moment. So if this thing, del, were a tensor, then we would expect, among other properties, we would expect some constant multiplied by this form, this one form, theta, some real numbered field times the vector field, and some other constant times the vector v. We would expect that to be linear in each of these real number products. This is a field, right? So at every point it has a vector. Well, at every point it's going to be multiplied by a real number, so it ends up being a function, but it's the same thing in principle. It should be linear in that. If it was truly linear, if it was a tensor, it would be linear in all of these things. So, well, what is this actually going to be? I mean, can we work this out? Well, it should. We're expecting it to be a f of x, f of space-time, b times del sigma, oops, not f, sigma x v, right, times the covariant derivative applied to all those three things. That's what it should be. The problem is that's not what it is. And the reason we can see that's not what it is because, I'll put a question mark there, it's actually defined to be sigma del mu of f of x, x of x. I'll put the x's back in there. Like, wait, this should be a u. Sorry, this should be a u. But it isn't. It isn't that, because what this is going to be is, oops, wait a minute, I need to add my A, I need to add my B here, right? I need to add those in there. So when we expand this guy out, what do we get? We get A theta, and then it's going to be the product rule. We're going to use the product rule in here, and we're going to get del B u acting on F times the vector field x plus F times the del B u acting on x, right? And then this mapping, this overall mapping here is linear, so this plus sign can split into two separate mappings. And the first mapping is going to be A sigma del B u f on, right, on, which is another function on x, plus A sigma f del B u on X, like that. And then these mappings are linear, right? These mappings are linear. So this should end up being A, B, if it's linear in B. Well, actually, it should be A, B, and let's see. It should be A, del, B, U on F, because this is a function, right? This is a function, so that should come out. And what's left is sigma on X, which is a real number, plus, and this should end up being A comes out, F comes out, B comes out, sigma del U on X. So this thing here, this part, A, F, B, sigma del mu on X, well, that's what this is, right? This is, remember, this thing here is defined as this here. So this term, the term we expect if this is totally linear, right, is this term right here. The problem is you also get this term right here. Notice, by the way, we use the product rule on the covariant derivative in the direction of BU. We use that product rule right here. I guess technically we did not assert that that product rule was true for this object. It turns out we want it to be true for this object. As part of the abstract definition, we force the notion of a derivative. It must obey the product rule. If it doesn't obey the product rule, in no sense can it be understood as a derivative. So the very fact that we want this thing to be a derivative, that we expect it to be a derivative, is that it will obey the product rule. And by the way, if you go back and you actually played around with, let's see, where was it? If you played around with the original definition, where is it? This guy right here. If you actually work this and you put in if you put in a constant here, you would see that this does in fact obey the product rule. Okay. So the existence of this term spoils it, right? This is what it would be if it was perfectly linear, and this is what you have. You have this, so that's the linear part, and then you have this nonlinear part. So it doesn't have obey linearity. But even on top of that, this thing here ruins it from being a tensor, right? Because that's not even a vector at a point. That's a field, and tensors just don't eat vector fields. So there are these two reasons why this operator, this covariant derivative operator, is not a tensor. Okay, so what if you do want the components of these things? What if you want the components? We now want to link up. What about these guys? What about the connection coefficients? Alpha, beta, gamma. What about those? Well, the way you derive those is you take the covariant derivative operator and you feed it a collection of basis vectors. You feed it, say, E alpha, E beta, and E gamma. And that will produce a real number, right? And that real number we will define as these coefficients. So, so for example, if I put in E0, E2, and say E1, that is defined as gamma 0, 2, 1. So that's how you extract these coefficients. So that's how you make the point of contact between this abstract notation and the coordinate-based notation. You actually choose a basis and you stick in these basis vectors one by one, generating every single one of these numbers. Now remember, when you do this middle one, right, E2, we're really talking about a field, right? It's E2 at every point X. It's a vector field. That middle slot has got to be a vector field. So this is at P, and this is at P, but this is a vector field. So again, proving that this thing here is not a tensor either, right? Because ultimately it's derived from this thing, which is a field. And I keep saying that point P, but remember from our old definition, we had P, and then we had a point Q, right? And we talked about the parallel version of the vector field at P. We have the vector field, which may be totally different, at Q, right? So that's the vector field. And then we have this thing here, which we call the parallel vector, right? And so the way this all works is this direction between P and Q, that is the vector U, right? That's at TP. So TP, there's a vector U, which sort of launches you in the direction towards Q, right? And then the vector field is measured all the way over at Q. And the vector field is also measured at P, but it's compared, this parallel vector over here is what is generated by these guys, these connection coefficients. So when I talk about at P, I'm talking about this point here. And this vector U turns out to be what launches it over there. And the vector field in this case, this vector field E2, is this thing would just be E2 at the point X, and then this thing over here would just be E2 at the point Q, right? So that's why it's a field, because you need to get E2 here and you need to get E2 here. It's the specific field of the second basis vector at the 2 points. So that's just a field like any other. But just remember, you're not just sticking in 3 basis vectors the way it implied. This is actually a function of x right there.
In fact, you can use this notation to look at something like this. E, J, E, K, right? And leave the last slot blank, right? And this object here has to end up being a vector, right? And that notation would be the vector that it is this vector. Oops. It's this vector. And so that vector has components. Well, what are those components going to be? Something like that. And this is a very good way of understanding intuitively what these functions of space-time are, what these connection coefficients really do. What they're telling you is specifically how does the vector field of the k component of the basis vectors, remember that's a vector field, ek of x, we just kind of went through that. Every point in space-time has, say, an E1 here, and then there's an E1 here, and then there's an E1 here. Every point in space-time has an E1, and that can be expressed as a vector field, you know, putting that E1 vector at every point in space-time. But the question is if you move a little bit in, say, E0 direction, how much does that, and so this ends up being the point P and then some point Q over here, how much does that E1 shift in the basis at Q? And that's what this is asking, right? And that's what this is telling, because this is a vector. And remember, we like to think of vectors when they change. That change is itself a vector, which is what this is, right? This guy here is a vector that represents the change in the vector field of basis vectors in the direction of other basis vectors. And you generally use this symbol only when you're talking about the coordinate basis, by the way. So it'd be more apt for this to be del J del K equals gamma alpha kj del alpha, and then that's actually del J del K gamma alpha kj del alpha. In other words, you don't usually put the del, or I keep saying del, the partial. You don't put the partial in the symbol for the covariant derivative. So, so this guy here, this del, this is understood as EJ, which is understood as that, right? And that ultimately is the connection between all of these symbols. But this is a really good way of understanding what the connection coefficients do. All right, so the last version of this notion of the covariant derivative I'm going to take from a book by Chandrasekhar called The the mathematical theory of black holes. Really great book. Hard though. And Chandrasekhar has his own presentation for the covariant derivative. It's nothing, ingenious. I mean, it's well written, of course, but it's not like he invented it. It's not like because Chandrasekhar is a legendary theorist in the field, the stuff we're talking about is so elementary. It would be like a legendary mathematician teaching you how to take the derivative of a function or something, right? It's very, very straightforward. He just has a slightly different approach. And it's also a blend of the coordinate-free notation and the coordinate notation. And he doesn't quite start as fully abstract as Wheeler does. He doesn't start all the way to the left here, but they both end up all the way to the right because ultimately that's what you need to solve problems. And ultimately in Chandrasekhar's book, he's fully committed to solving the mathematical theory of black holes. So he spends a lot of time here, more so even, I think, than Wheeler, although, like I say, it's totally up in the air about how much time one spends in one place or the other. The point being that this is a slightly different blend of an approach, and I thought it would be interesting to show. What Chandrasekhar does is he starts with delta, or this gradient symbol, and he calls this thing the affine connection, right? And the word affine sometimes pops into the theory in older books a lot more than newer books, or the other way around. The point is you have to understand what these mathematical objects do and are. And this is, of course, the exact same object that we introduced in the Wheeler section. But the affine connection is, he defines it as a map that takes vector fields, so I'll say a vector field X, and produces an object, let me change that actually, vector field, I'll take Y, and it produces an object that looks like this, which is also then defined as an object that takes vector fields, say Z, and it gives other vector fields, and this other vector field is called the covariant derivative of Z in the direction X. But this is a vector field. The point is that this guy maps vector fields to vector fields. This guy maps vector fields to objects that are maps that take vector fields and give vector fields. Well, what kind of an object is a map that takes a vector field and gives you a vector field? Well, that kind of object is a 1-1 tensor. Right? So this ultimately here is a 1-1 tensor. So this object is a map that takes vector fields and gives you 1-1 tensors. You know, if I'm going to use, I should have used X here, actually, right? Because it maps X to this object where X lands in the substrip, right? And then this object will take Z and will give you this thing, right? So it's a 1-1 tensor. So once he defines these ideas, he says, well, this is what we're after. We want something that takes the derivative of a vector field and gives you a vector field. A vector field should be a derivative of a vector has to be a vector, because the way vectors change in our normal way of thinking of little pointy things is, you know, if a vector is changing from there to there, that difference is somehow accounted for by another vector here, right? So this little thing here should somehow reflect the derivative of this thing as it changes from this to that, right? So you're expecting the derivative of a vector to be a vector. And then on top of that, a derivative has certain properties that we demand that this thing have. So what are those properties? Well, the first is delta, or this covariant derivative in the direction of x of some vector field y has to be linear in x. We want it to be linear in everything. So the first thing is x, which means that if I had some function times the field x plus another function times the field z, and I put that in the subscript here and operated on y, I expect this thing to equal this. I expect it to equal this, right? It's linear, and these things now are functions of space-time, right? Because remember, x is a vector over the manifold. These are functions over the manifold now. So I expect this linearity. Then the other thing I expect is it to be linear in y, right? So I expect this. Right? So that's two properties of linearity that are very critical. Then I want to define this for functions. So I want to say that this object, when it acts on a 0, 0 tensor, is going to be the vector field in question acting on the function. Remember, these vector fields are understood to be differential operators. This is a differential operator. So it can act on functions. So when all you're dealing with is a function, you're just taking that differential operator, acting on the function, and you get another function out. And that's the right thing, because the derivative of a function is also going to be a function. So this is good. So this is part of our requirements. And then the last one is sort of the big one, the Leibniz rule, which says that this 1-1 tensor, when it acts on a function times a vector, has got to give us the thing acting on the function times the vector plus the function with this mapping acting on the vector, right? And that's pretty important. So what we're looking for is some object delta. Let's see, I can't go any farther. I keep saying delta, but I don't mean delta. What I mean is basically I mean this 1-1 tensor. We're looking for this 1-1 tensor that satisfies these rules. So such a thing does mathematically exist, and it would be called a derivation if it does. And there's lots of different things out there that are derivations. And there are 3 different ways of accomplishing these rules that I know of in the field of differential geometry. One is the covariant derivative, which we're studying today. The other is the Lie derivative, and the third is the exterior derivative. So there's 3 things that naturally solve these properties, and we use all 3 of them in the study of differential geometry. This one, of course, is probably, well, it's hard to say which is the most important, but this one is the one we're starting with. So these properties of linearity, that's where we're going to begin. So now what he does is he chooses a dual basis of vectors, EI and EJ. This is a dual basis, and if we were in the coordinate basis, EI would correspond to del I, and EJ would correspond to dxj, right? And we will eventually pop into the coordinate basis, but we're just going to use these abstract terms for now. And so when I write down del x of y, I can always say, well, y is a vector, right? So I just go del x, yi, or yj, ej, right? Just like this. And then I use the Leibniz rule, and I pop out x acting on yj, oops, undo, ej plus yj with this 1-1 tensor on ej. And if you look, this thing here, these are functions of spacetime. The components are functions of spacetime because this is a field. So these functions of spacetime, because of that linearity we showed, comes out because this thing is linear, right? This operation is linear, so it comes out. But before it comes out, this thing, we operate the Leibniz rule. So this will operate on these functions of spacetime. But we know that is defined as just the vector field applied to those functions, and that's what this is. And then this is the ultimate vector, which leaves here. And then the other half of the Leibniz rule, we actually do take the yj out, and then we operate on the vector field itself, and we get this thing here. And that thing here is, of course, what all the trouble is, because this is this is an unclear object, right? We think this is a 1-1 tensor concept, but ultimately we're trying to figure out what this thing is. So all of the mysteries wrapped up in here. We know what this is, and we know what this is. This is a little unclear. So the next step is to take that lack of clarity and sort of jam it up into something that we do understand, or something that we can wrap our heads around. I don't say we immediately understand it, but this guy we're going to rewrite as this. And so what have we done? Well, taking a look at this, we know that this thing here has to be a vector, right? And it almost looks like a vector because you have this j summed over a j, and that's a component, right? But remember, this is a process. This thing here acts on this, so we don't know what it leaves over. But what ultimately this whole thing has to be is a vector. So this thing here has to sum into this thing here. Ultimately, that j has to sum into something that this produces. Hopefully it leaves a j behind, and the result has to be a vector. Well, this object, for a particular basis, therefore we can understand it to be what amounts to a 1-1 tensor, right? It has to ultimately eat this vector field and produce something that can sum over this j. And it has to ultimately end up being a field that can sum over j and leave behind a vector. So it kind of looks like a 1-1 tensor. So we rewrite it this way. We say here's our vector component now, right? And it's summing over another component. And that component has to have another index that sums over this index. And so whatever this object is, it has to be writable, it has to be understood in this form, where this is some kind of function that's dependent on whatever this x is, right? So we usually call those omega, the symbol that he gives is omega for this. It's got two components. It in itself is a two-component object that is a 1-1 tensor waiting for a vector to feed into it to give it back another vector. And this is that expression. And notice it's got two components, and it's a function of the vector field, right, that goes in here. So this object isn't in itself, strictly speaking, anything we can clearly understand from what we know, but it expresses all of the requirements to make this thing here ultimately a vector. And so now we rewrite this as the covariant derivative in the direction x of y, x, y, j, ej, plus yj times these coefficients. And again, you'll notice that there's a tendency to separate these things, this L to the left and J to the right, this giving it some ordering. But we can't immediately use that as a basis of thinking that this is some kind of tensor object, because it's still just sort of a set of coefficients, right? You have to prove that it's a tensor object. It is just, though, common to sort of lean it this direction, because ultimately it's going to be related to the connection coefficients we learned about in the last lecture. So with this in mind, we now have compressed all of the strangeness into these things right here. Now we could take this one step further, and up here where we had this expression, we could have done this. We could have said yj del xk ek ej, like that. And then we could have pulled out the xk because of linearity, and we could have gone xk y j del ek ej, like that. And then we could have taken this whole thing here, and that's what we could have called, let's see, what would we have called it? We would have called it omega L
J, E, K, right? Which is pretty obvious, right? It's the vector field X simply gets replaced with the unit vector field, or not the unit vector field, but the basis vector field, and xk comes out in front, right? So we could have done that. Then this thing here, we could just have renamed omega L J K, right? And ultimately, that is going to be the connection coefficients, L, J, K. So that's another shortcut we could have taken earlier by using our vector expansion, xk, ek, right there, and then the linearity of things. But anyway, going back to this, if I swap the names of the indices, I have j summing over j here, and but if I swap the indices so that this is L and these are J, that's a meaningless change, right? That if I write this as Y L omega J L X E J, I haven't done anything material. All I've done is change the symbols. But what it does allow is it makes it more evident that this J and this J are the same, so I can actually pull it out. And ultimately what that will allow me to write down is del x y equals x y j e j plus y l omega j l of x. And I can erase this ej here, put this in brackets, and pull the ej out. And now you see that this guy is a vector, right? This is the component, right? And this is the basis vector. And that's actually what we're after. Although we haven't really accomplished all that much except to cram the lack of clarity into this thing right here. So now we just do this, we just go into the coordinate basis, right? And we write this like this, del k. This is now the coordinate basis of y, which equals, right? I'm replacing the x with this guy, right? That's just making the substitution of the coordinate basis, which is now this derivative operation, right? This is the differential operator, plus, let's see, y L, and then it's omega J L partial K, like that. And then this presumably would now be in the basis. Now this EJ becomes partial J. And now the whole point is that this thing here is the jth component of this vector. And this guy here, using our other notation, using this notation here, becomes omega L J K. And so now that's what we're going to call gamma L J K from our previous work, and we end up with exactly the expression we expected, which is del K Y J plus y L gamma J L K, like that. And that is our original covariant derivative notion. So this is a way of walking through it using a much more axiomatic approach, right? You're starting with these axioms, and you drive yourself into believing this thing. Ultimately, you still have to supply these numbers, though, or these fields, right? You still have to supply this. That is up to you. And that's what defines the connection on the space-time. So again, we've just crammed all the mystery into these expressions. So now we've looked at
this notion of the covariant derivative from three different perspectives: from the coordinate-based perspective, from this axiomatic perspective of Chandrasekhar, and also from this very abstract perspective of Wheeler. They all have their value, but I think the most important one was the first one we did in the last lecture, right? So this is sort of an augment of that last lecture, and that's why I'm writing in the show notes that this is all pretty optional. But this notion here is actually very helpful, because when we talk about the lead derivative and the exterior derivative, you're going to see that we're going to be able to create two other derivatives that follow these axiomatic ideas. The difference is in each case, you have to assume something, right? You have to assume something. You don't get a derivative for free. And here, in this case, you needed the connection coefficients, right? We have to add that, or else we can't make a sensible derivative. If we can't understand parallelism, we cannot make a sensible derivative. So we have to add the connection coefficients. And that's the special add for the notion of the covariant derivative. There are other objects that obey these rules that you have to add something else. For the lead derivative, there has to be a preferred vector field, we'll see. And for the exterior derivative, you have to assume that whatever you're operating on is anti-symmetric. So there's all these different little things for these three different types of derivatives. But right now we've covered the covariant derivative, and then I'll move on to the lead derivative in the next lecture or the one after that.